Brilliant. Yeah, so I'm going to talk to you a bit about epidemiology of red needle cast, just a little bit, and then the research we've been doing around control. So the talk overview, I was going to give an introduction to red needle cast, but I don't think I need to now. Thanks, Mike. But I'll touch on that a little bit. I'll talk about the research aims and approach that we've taken in terms of controlling this disease. A little bit about epidemiology, as I said, screening of chemicals. I'll demonstrate that copper is showing some promise as a control agent, and outline some further work that is needed. So, as Mike said, it's caused by Phytophthora pluvialis, which is a fungal-like microorganism, but not a fungus, something a little bit different. And kind of, it's new to science as well. It's only been known for about 10 years, and it doesn't cause any problems anywhere else in the world. It's only a problem really in New Zealand. It has been found in the northwest of the US, and that's where we think it is native. It expresses across winter. We'll see more of that in the next slide. And significant growth losses have been demonstrated in at least one study after defoliation. However, repeated defoliation is rare. Kind of usually on one stand, it'll come back maybe every 2 to 3 years, but it can happen repeatedly at sometimes. It's mostly a problem in the central North Island and the kind of northeast coast of the North Island and up in Northland, and also at the top of the South Island. But it's been recently been found down near Dunedin, so kind of wait and watch and see what happens down there. Research aims. The objective of this research was to develop a cost-effective chemical treatment for red needle cast, so that industry can manage R&C in its existing stands. The benefit being increased productivity, protection of these at-risk stands, and retaining license to operate. So the research approach covered different areas. In terms of epidemiology, we have long-term monitoring of disease expression, so we have about 50 sites that we monitor every year across the North Island, looking at when and where disease expresses. We look at when spores are released, and we've got trials at the moment looking at when infection happens. So we can work out when we need to protect the plants in terms of within the year, but also which year do we need to protect plants. In terms of chemical control, we've screened potential active ingredients in the lab and in the field, and taken those into further trials with the most promising chemicals. We're also doing work which should enable a cost-benefit analysis, so we're looking at the impact of disease on growth, so we've got a few trials doing that, and also we need to look at the benefit of spraying. And all of this we want to integrate together into a decision support tool for foresters, which will hopefully support a decision on whether it's necessary or beneficial to spray. So first, just a couple of slides on epidemiology. So this is data from our diagnostics lab, and this just shows the pattern of detections in the diagnostic labs for the last 10 years. And basically, you can see a peak in the middle of the year, every year. This is an average for kind of the whole of the country, but as I said, it's a winter expressing disease. And this gives us some clues about when we might need to protect the foliage. We also have some information on terms of when spores are released. So the graph on the left-hand side is from the one site in the central North Island from 2012 to 2014. And we have the graph on the right is from one site over on the east coast. And basically you see that the spore dispersal, or the sporulation, happens about the same time as we see the symptoms as well, so peaking at the end of winter. But there is variation between years, and there is variation between sites and within sites. So it's not an easy thing to work with, as Mike said. But this gives us an idea within a year when we might need to protect the needles using chemicals. So moving on to chemical controls, we started by looking at 12 different active ingredients in the lab in Petri dishes. And this table just shows that 11 of them showed promise. So zeros mean no growth, ones mean the same amount of growth as controls. So you can see 11 active ingredients inhibited entirely the growth of the fungus or partially. So we took on 3 of those, which are widely used, metalaxylyl M, phosphite, and copper oxychloride, and sprayed trees with the different active ingredients, and then in the lab inoculated the detached needles with Phytophthora. And you can see from the graphs, all 3 active ingredients were effective in reducing symptoms. So the white bars show the controls after 6 days and 90 days, so phosphite at the top, copper oxychloride in the middle, and metalaxylyl M at the bottom. So it all showed promise in these assays. So we first moved on with phosphite, which is widely used in nurseries to control Phytophoras, and it's also used in the avocado industry. This is from field trials where they sprayed trees in the field and then brought needles back into the lab and did the same in-house inoculations. Well, not unfortunately, but phosphite was ineffective when sprayed. So that's what the graph on the left shows. On the right, it shows when we did stem injections with phosphite, it was effective at reducing the impact of disease. This doesn't have any operational practicality, but it is useful for our research projects, and we are using it at the moment to look into impacts of red needle cast. We then switched to looking at copper, as phosphite didn't show any promise. And so this is data, again, from detached needle assays on the left-hand side, just showing the sprays at the dophystroma level and twice dophystroma level both control red needle cast on potted plants. And then on the right-hand side, we've got the graph shows whole plant inoculations where we inoculated whole plants and then we kept them in our fog rooms under optimum conditions for the disease. And we did 2 inoculations on them, and the dophystroma standard significantly reduced disease levels. We've then also done some copper operational field trials at Kinleaf, which were initiated by Mike Baker. And these have, this is data from 2017, where plots at 2 sites in Kinleaf were sprayed in February with a dophystroma standard, and that significantly reduced the severity of disease symptoms in the canopies, and it also, at one time point, significantly reduced needle cast. We've also put together a cost-benefit analysis tool, so this was work of Robert Radich at Scion as well. So a lot of the assumptions in this at the moment we need to do further work on to get kind of more a better understanding of some of these assumptions, but basically you can use this as a tool at the moment to work out the cost benefit of using copper, but we are working on improving these assumptions. And I think Robert's here tomorrow if you want to talk to him about that. And then that just leads me to further work. So we need to know kind of when to spray. We know when spores are present within a year, but we don't know exactly when infection happens. Does infection happen in a narrower band of the year than inoculation? And so that'll inform us in terms of when needles should be protected. We also need to know there's so much variation between years and between regions when to spray, and kind of, so we want to develop a kind of forecasting system for red needle cast for site-specific decisions. We need to have a better understanding of the impact of disease and the impact of spray on that to enable a better cost-benefit analysis. And we also need to do further research on other management tools such as resistance, which Natalie's going to talk about, silviculture, and potentially alternative chemicals, which all leads towards a decision support tool for forest managers. So I'd just like to acknowledge some of our techs in the lab, some of our industry partners, and just highlight some of our research outputs, which are available as papers. And thank you very much.